Imagine you are given a specific fact about a population, and you immediately pull a sample to test it. You are standing in front of a basket containing 200 opaque plastic bubbles. The baseline assumption, the rule you have been told, is that exactly one of those bubbles contains a $100 bill. If that assumption is true, the probability of reaching in and pulling out the winning bill on your very first try is exactly 1 in 200, or 0.005. If you actually pull that $100 bill on attempt number 1, your immediate reaction is not to think you are incredibly lucky. Your reaction is to doubt the initial rule. You suspect there are actually more $100 bills inside the basket. In statistics, this is called a rare event. The sample data, your winning bubble, contradicts the initial assumption, which we call the null hypothesis. But data science requires precision. We cannot rely on a gut feeling to decide if an outcome is rare enough to disprove a baseline assumption. We require exact probabilities. We use established mathematical distributions to calculate precisely how likely our sample data is, yielding a single number known as the p-value. Those p-values are then weighed against strict numerical thresholds. There is no room for interpretation. The decision is entirely binary. Hypothesis testing is the formal mechanics of this process. It quantifies exactly how unlikely your sample data is, under the strict assumption that your initial belief was true. To calculate that precise probability, the first step of any hypothesis test is mapping our known sample data to the correct geometric probability shape. If we are testing a population mean, and we actually know the population standard deviation, we plot our data on a standard normal distribution. In the far more common scenario where the population standard deviation is unknown, we use the sample's standard deviation as an approximation and switch our model to a student's t-distribution. And if we are testing population proportions, we can use a normal approximation, provided we have enough independent trials to meet the conditions of a binomial distribution. Selecting the wrong model invalidates the test entirely. The specific shape of the distribution dictates the exact mathematical area under the curve. The variables we hold, like standard deviation and sample size, lock us into a specific environment. We cannot measure a rare event until we build the right map. Let's apply this environment to a claim. A baker insists his bread height averages more than 15 centimeters. That is our alternative hypothesis. The null hypothesis, the baseline we assume is true, is that the mean is 15 centimeters or less. We pull a random sample of 10 loaves and measure them. The sample mean comes out to 17 centimeters. From historical data, we also know the population standard deviation for the bread height is exactly 0.5 centimeters. Because we are testing a mean and the population standard deviation is known, we map this directly onto a normal distribution, anchoring the center peak at our assumed null hypothesis of 15.
However, we are dealing with a sample mean of 10 loaves, not a single loaf. The central limit theorem dictates that we must divide our standard deviation by the square root of our sample size, giving us an adjusted standard deviation of 0.16. This physically alters our probability model. The curve pulls inward, becoming tightly clustered around the mean. We now ask the mechanical question: if the true average height is exactly 15 centimeters, what are the odds of pulling a sample mean of 17 from this specific curve? We plot our sample mean of 17 on the x-axis. It lands deep in the far right tail of the distribution. The probability of getting a result this extreme, or more extreme, is represented by the remaining area under the curve to the right of our marker. This geometry is the p-value. Here, the p-value is approximately 0. Almost 0% of samples would land this far out by random chance alone. The microscopic physical area remaining under that tail is the definitive proof. The geometric evidence contradicts the baker's null hypothesis, giving us the mathematical authority to reject it. Small is a subjective concept. A statistician cannot simply look at a calculated p-value and decide it feels rare enough. We require a rigid threshold known as alpha. Alpha defines the exact probability of making a type 1 error we are willing to accept. The logic gate operates on 2 tracks. If established alpha is greater than your calculated p-value, you reject the null hypothesis. The standard memory heuristic that this mechanic is simple. If the p is low, the null must go.
Conversely, if alpha is less than or equal to the p-value, the results lack significance, and you do not reject the null hypothesis. Failing to reject the null is not the same as proving it is true. It simply means your sample data lacked the mathematical weight to destroy the baseline assumption. Alpha serves as the ultimate arbiter. It strips human bias from the equation, forcing the researcher to accept whatever binary output the numbers dictate. Consider a genetics lab testing a population proportion, claiming their new procedure results in a boy being born more than 50% of the time. The null hypothesis locks in at exactly 0.50. Before drawing any samples, the researchers set a strict alpha threshold of 0.01. The test is run, the proportion distribution is mapped, and the final calculated p-value comes back at 0.025. We compare the probability against the threshold. 0.025 is greater than 0.01. Because the p-value failed to cross below our preset barrier, the logic gate shuts. We do not reject the null hypothesis. In practical terms, a 2.5% chance of this result happening randomly might sound small, but it is not extreme enough to meet the lab's own rigorous standard of proof. By mapping the correct distribution, calculating the exact geometric area of the p-value, and holding firm to a preconceived alpha threshold, hypothesis testing replaces subjective doubt with objective reality.